Let's make a couple of points about predictability of the mesos, and that basically means the concept of predictability is something you should be familiar with. It's almost always a model concept. How predictable is a particular phenomenon like El Nino or monsoon intraseasonal oscillations? And predictability usually comes from having memory from somewhere. For example, we said weather forecast is a chaotic problem. After a few days, errors in initial conditions can grow and the weather becomes unpredictable. Tropical weather predictability is different than the mid-latitudes, and ocean memory gives us predictability of the second kind, where even though weather becomes unpredictable after a few days, we can still make seasonal to interannual predictions. For example, in the case of El Nino, and El Nino's predictability comes from the fact that it's a coupled phenomenon and the ocean is moving heat back and forth slowly, so the coupled response has got a systematic trajectory which can be predicted. In the case of mesos, this is the example from Dwayne Walliser's chapter in the same book, Lau and Walliser, and it's basically showing timelines here and the longitudes here. So obviously that's eastward propagating things like MJOs, obviously. Uh, it's not very important the details of what is being shown, but basically the total OLR and filtered OLR are being shown to identify the westward propagating Rossby waves and eastward propagating Kelvin waves, and of course in the atmosphere there are also Doppler shifted Rossby waves which can go in either direction and so on. So the fact that these features take days and weeks to propagate tells us that if there is a way to capture those signals, then there is predictability, there is memory in the system. Okay, that's a very short way of saying it. So they are basically looking at OLR data starting on April 1st and then using the forecasts for days from April 1st to depict this picture. The chapter is on predictions and predictability, but here I'm going to just keep it short. So typically what we do is to look for predictability by using statistical patterns in the mesos, for example. This is MJOs, but we will switch to mesos. And the extended EOFs or nonlinear Laplacian spectral analysis, for example, here from Sabir Ali's paper. And extended EOF was proposed by Suhas and Nina and Goswami, parallel to the MJO index. We already briefly mentioned the MJO index in terms of the EOFs of coupled EOFs of winds at I think 850 hectopascal and 200 hectopascal and OLR to look for phase propagation of the MJOs, and there is an index called Wheeler and Hendon index, which is the real-time multivariate mode index or whatever. So the statistical patterns can also allow you to make statistical predictions, but they can also allow you to kind of see where the signal to noise ratio can be maximized so that predictability and predictions can be improved by using those sorts of indices to capture mesos. So this is just showing the reconstruction of the meso evolution for the period of June 2004 to September 2004, one particular season. Spatiotemporal maps represent the GPCP rainfall anomalies obtained from the NLSA, which is the nonlinear Laplacian spectral analysis of meso indices. And you can see here it's starting here in on June 1, June 10th, June 20th and 30th and so on, and you can see what we saw before in terms of the rainfall being below the seasonal mean. So active period here, break or subsidence over here, switching to active period over there, and sorry, break period over there, and active period or ascent over the ocean, and so on. This paper argues that their index with the NLSA approach is better than the extended EOF approach, and the prediction experiments using the coupled forecast system of NOAA is shown here for modes of MISO 1 and MISO 2. So that basically argues that again, extended EOF mode, MISO 1 and MISO 2 have predictability out to, I keep losing my cursor here. Somebody suggested again that I should use a laser pointer, but nonetheless, here are the correlation values, and that's the 0.8 line, which shows that there is predictability out to several weeks or several pentads, which is pretty impressive for active break periods. The threshold above 0.8 is considered a usable prediction, right? And the RMSEs are shown here, which increase with lead time, of course, and you can also choose a threshold for RMS errors compared to observations where the signal predicted can be considered useful for agriculture or health, water resource management, and so on. Okay. What else can we say? In the real world, though, you want to make predictions based on dynamic models, then the system gets complicated. So this is the Indian Institute of Tropical Meteorology and IMD, India Meteorology Department's extended range prediction and dissemination system. So the system is initialized, it generates perturbed atmospheric initial conditions from that, and uses multiple resolution configurations of the CFS as well as GFS. So that's the coupled forecast system, and this is the global forecast system, which is forced atmospheric model with SSTs taken from the model, which are then bias corrected. So the model predicts SSTs which has biases with respect to observations, which are corrected using some methods, and then a multi-model ensemble is generated in terms of forecasts at interseasonal or extended range forecasts, weeks 2 to 4. And there is some post-processing and bias-corrected forecast products that are generated, which include things like active break periods, MISOs, MJOs, heat waves, cold waves, predictions for northeast monsoon, not just for monsoon interseasonal oscillations in the summer season. Cyclogenesis is also generated out of these post-processed products, and applications are done using these forecast products for agriculture, extremes, hydrology, energy, health sector, urban planning, and so on. So this goes to the framework developed by WCRP under the S2S prediction projects and applications. And obviously the crux of the matter, or the proof of the pudding, is in the application. How useful are your forecasts for actual applications? That always makes a big difference. The other thing that is done once you have such a dynamical forecast system is to see if there are ways to improve predictions. Okay, so one of the approaches tried in addition to the multi-model ensemble here is the so-called multi-physics ensemble, where, remember, we said the convection parameterizations in the models are multiple. They are chosen based on various criteria, and there is ways to use each parameterization. People do different kinds of weighting based on which one does better on the ocean, which one does better on the atmosphere, on land, which one does better in the tropics, which one does better in the subtropics, and so on. And again, I'm not going to spend too much time, but this is another paper from the Indian Institute of Tropical Meteorology group, and it shows the phase mean of the multi-physics ensemble of multiple convective parameterizations for pentads 1, 2, 3, and 4, and is computing correlations with observations. And you can see the correlations are pretty impressive, but in addition they also look at the distribution of rainfall bins in observations here and in the model forecasts for each pentad, and they argue that the multi-physics ensembles systematically improve forecasts and extend the predictions out to multiple pentads. So you are basically treating this as an engineering problem where you use whatever methods you can to extend the prediction skill, increase the prediction skills and extend the prediction lead times to multiple pentads, and then again you see if that helps the applications as well. Okay, so that's a brief take on the predictability and predictions of MISOs. This is a similar method that's used at other time horizons as well, but going from weather to climate, this bridge in the middle called subseasonal timescale is where lots of applications are possible in the so-called Ready, Set, Go framework, which I have a course on S2S applications on my other channel that you can check out, and that is growing more and more, and that's a good way of actually even dealing with extremes and climate change impacts as they are already happening in the domains like the monsoon or even in the mid-latitudes, wherever there is predictability in the S2S time scale. Okay.